Hello friends, Mr. Burrell here. We're in the last lesson we're going to have for Unit 12. This unit has been shortened a little bit for quarantine purposes, but we've talked so far about the parent functions of sine, cosine, and tangent functions and what those graphs would look like. We've talked about how we can identify transformations of a trigonometric function as far as changes in the midline or a vertical shift, and changes in the amplitude, how high and low the maxes and minimums on a graph will reach. So now in this lesson we're going to talk about the period of trigonometric functions and how we can identify changes from an equation and a graph to the period of a trigonometric function. So by the end of this video today, this is what I hope you're able to do. Determine the period of a equation from the trig equation, graph the period from a trig equation, and write the equation of a trig function with a period change given a graph. So if I give you an equation, I want you to be able to graph the period. If I give you a graph with a period change, I want you to be able to write what the equation would be. So that's what the idea is by the end of this video. So first of all, let's remind ourselves what period means in relation to a trigonometric equation or a function or a graph. What does period mean? So the period is the distance required for the function to complete one full cycle before it begins to repeat itself again. So if you remember on our sine and cosine and tangent functions, let me bring over my graph here. I'm just going to pop up the traditional sine wave. The period of a sine function or a sine wave is 2 pi radians or 360 degrees because it takes 2 pi radians or 360 degrees to completely repeat itself. Same with a cosine function. It starts at its maximum here, and it takes 2 pi radians or 360 degrees to make one full cycle and get back to that maximum again. For a tangent function, it's slightly different. It takes pi radians or 180 degrees for it to repeat itself. You can kind of identify that from each of these points. It starts at 0, 0, pi 0, then 2 pi 0, 3 pi 0. Every pi radians or every 180 degrees, that tangent function will repeat itself. So right here I have my sine and cosine period is either 2 pi or 360 degrees, and tangent period is pi is equal to 180 degrees. Again, the period is the distance required for the function to completely repeat itself. So if theta, so if I have a function like y equals sine of theta, if theta is multiplied by a constant, then the period changes. So previously, we talked about how I could have a times sine of theta. That would change the amplitude. We talked about how if I added a constant on the outside here, that would change the midline or the vertical shift. Now, if theta is multiplied by a constant, call it b. So if theta in the actual sine function is multiplied by a constant, then the period changes. So we've talked about amplitude changes, midline changes. Now, if theta is multiplied by a constant, we're going to be talking about a period change. Okay, so to find the period from an equation, previously it's been pretty easy to find the midline and to find the amplitude. This is going to take a little bit of an extra step. So to find the period from an equation, divide the parent graph period by the coefficient of theta. So for example, if I have y equals sine of b theta, this constant multiplied by theta, then in order to find the period of that function, we're going to take, for a sine or a cosine function, 360 degrees divided by b, or 2 pi divided by b. So to find the period of a sine or cosine function, we take the period of the parent function, which is 360 degrees or 2 pi, and divide by b, this coefficient in front of theta. And that will give us the new period, the period of the transformed function. For a tangent function, since the period of a tangent function is 180 degrees, or pi, to find the period of a tangent function, we take 180 divided by b, or pi divided by b, depending on if we're dealing with radians or degrees. That's how I determine the period of a trigonometric function. So let me show you kind of what that is going to look like. So on my graph here, like here is y equals sine of x, and I have sine of bx here. You'll notice this bx, and I have this slider here where I'm going to be able to change what b is. Right now, b is equal to 1. So notice what happens to this graph as I make b bigger. What do you think is going to happen? So as I make b bigger, look at that. The period gets smaller. So it takes less and less distance, less and less time for the function to repeat itself. And as I make b smaller, so if I go all the way back here to 1, that's my parent sine function. What happens if I make it smaller, if I make it a decimal? Kind of horizontally stretches it out. So it takes longer and longer for the function to repeat itself. The period gets bigger. So the bigger the b value, the smaller the period. The smaller the b value, the bigger the period. And that's going to be the same with cosine. Notice here, as b gets bigger, the period gets smaller, etc., etc. And with tangent. Ooh. Well, look at that. Isn't that cool? And as b gets smaller, the period gets bigger. Okay. So now that we can kind of visualize that a little bit, let's look at some sample problems. So first, I'm going to start off right off the bat with some problems from your homework assignment. So part of the homework assignment just has you finding what the period is. Not graphing or doing anything, just finding what the period is. So here it says, using degrees, find the period of each function. So remember, period is for cosine and sine, period is equal to 360 over b, or 2 pi over b. For tangent, the period is 180 over b, or pi over b. So for degrees, my period of this cosine function is going to be 360 degrees divided by 4, because b is equal to 4. Well, 360 degrees divided by 4 is 90 degrees. So my new period for this graph, for this function, would be 90 degrees. It takes only 90 degrees for that function to complete one full cycle. Okay, and that was homework problem number 1. For homework number 9, I have y equals tangent of 8 theta. So the period of a tangent function is 180 degrees, because we're talking about degrees, divided by 8, or divided by b. So 180 divided by 8, my period for this function is going to be 22.5 degrees. So it only takes 22.5 degrees to complete one full cycle. Really short time to complete one full tangent cycle. Okay, here this next section, this is homework question number 7 and number 11. For these ones, we're going to be using radians to find the period of each function. So for cosine, the period in radians is going to be 2 pi divided by b. And in this case, I have theta over 6, which is the same thing as writing cosine of 1/6 theta. So b is 1/6. So I need to do 2 pi divided by 1/6. Well, when I divide by a fraction, I can multiply by the reciprocal. So this is the same thing as 2 pi times by 6 over 1. Well, 2 pi times 6 is 12 pi. So the period of this function, cosine of of theta over 6, is 12 pi. It'll take 12 pi radians to complete one full cosine cycle, one full cosine wave. For number 11, y equals tangent of 6 theta. Again, period for a tangent function is going to be pi over b, or pi over 6. And that's a reduced fraction. So the period for this tangent function is going to be pi 6th radians. So instead of pi radians to complete a full tangent cycle, it's going to be pi 6th radians to complete a full tangent cycle. Okay, so now we have a little bit of practice with identifying what the period of each of these functions is going to be based on the b value that's multiplied by theta here. So let's practice graphing them. So again, using degrees or radians, find the period of each function, then graph the function. So the period of a sine function in degrees, because we have degrees here, the period of a sine function in degrees is 360 degrees divided by b, or in this case, b is 1/2. So 360 divided by 1/2 is the same as 360 degrees multiplied by 2 over 1. So 360 times 2 is 720 degrees. So instead of just taking 360 degrees to make a full cycle, it's going to take 720 degrees. So my traditional sine wave would look like this. It would take 360 degrees to go up, down, and back up again here, and it would split right at, touch the x-axis again at 180 degrees. So for my new sine function, sine of theta over 1/2, it's going to look something like this. And again, this doesn't have to look exactly perfect, but my amplitude should still be 1, my midline should still be at x equals 0, and my period should be 720 degrees. So it took 720 degrees to go through one full sine cycle, one through sine wave. Okay, let's look at this one, sine of 4 theta. Well, the period of a sine function is 360 degrees divided by b, or 360 divided by 4. 360 divided by 4 is 90 degrees. So my period is 90 degrees. So here's a 90 degrees, 90, 180, 270, 360. So it's going to take 90 degrees to get through one full cycle. So again, this is going to be perfect, but it's going to look something like, something like that. Whoop, 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 whoop. Takes 90 degrees to get through one full sine wave, just like that. Midline hasn't changed, the amplitude hasn't changed, but the period has. So instead of taking 360 degrees for one full cycle, so traditionally my sine wave would look something like this. So instead of taking 360 degrees for one full sine wave, only 90 degrees. Okay, now these are still in degrees here, so using degrees or radians, find the period of each function. So for these cosine functions, the period is still going to be 360 over b. So in this case, 360 over 4. So the period of this one is like number 2 on the previous slide. The period is going to be 90 degrees. So here's 90 degrees, 180, 270, 360. Every 90 degrees, I'm going to repeat a cosine wave. So my cosine wave starts at my maximum. It better end up again at a maximum. So my cosine wave is going to look something like that. Whoop, 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 whoop. Again, not completely perfect, but every 90 degrees here, I should have a full cosine wave, which I do. So again, the period is the time it takes for a function to complete one full cycle. So my cosine wave completed one full cycle in 90 degrees time. Midline is still at x equals 0. Amplitude is still at 1 and -1. Okay, cosine of theta over 4, my period is going to be 360 divided by 1/4, because my b value is 1/4. Well, 360 divided by 1/4 is the same as 360 times by 4 over 1. 360 times 4 is 1,440. Woo! That's a big number. That's right here. They've kind of condensed this graph for us. So it's going to take 1,440 degrees for this cosine wave to make one full cycle. So from here to here. So my cosine wave starts at a maximum, ends at a maximum. It better hit its minimum halfway between 0 and 1440 at 720. So it's going to look something like that. Might keep going here like this, etc., etc. Notice how much more stretched out this function is than this function because my period is so big. So in 1440 degrees of time or distance, I completed one cosine wave like so. Okay, so those were, if I gave you an equation, you could find the period and graph that function. Now, if I give you a graph, we're going to use the graph to find the period and write what the equation would be. So keep in mind, both of these look like either sine or cosine waves. So the period is going to be, and I have these in radians. These angles are in radian measures. So my period is going to be 2 pi divided by b. Okay. So this right here, I started a maximum. So this is going to be a cosine wave. So here's one full cosine wave. So my period is what? My period here is pi. So it takes pi radians to go through one full cycle, one full cosine wave. So my period here, I know, is pi. Well, I need to solve for b. What is my b value going to be? I need my function to look like this. Y equals cosine of b theta, because my period is changing, so that b value needs to change. So how am I going to solve for this b value? Well, I'm going to go ahead and multiply by b on both sides, because that'll cancel out b in the denominator over here. So then I'll have b times pi is equal to 2 pi. And then in order to get b by itself, I'm going to divide by pi. 2 pi divided by pi, those pi's cancel, and I'm left with b equals 2. So my equation is y equals cosine of 2 theta. Y equals cosine of 2 theta. So if I'm given the period, you can think of being able to find b by taking the period of the traditional parent function divided by the period of the transformed function. So if I had p equals 2 pi over b, I can find the period if I know the b value, and then here I can find the b value if I'm given the period. You don't need to memorize this formula. If you have this one, you should be good, but this one can be helpful too. Okay, let's look at this next one, number 2 here. So I'm starting at 0 here. I'm starting at the origin, so I know this is going to be a sine function. So let's say I go through one full sine cycle here, and I reach 4 pi. So my period is equal to 4 pi. Well, since period is equal to 2 pi over b, I'm going to go ahead and multiply by b on both sides. And then I'm going to divide by 4 pi on both sides. Well, 2 pi divided by 4 pi is 1/2. So my equation is y equals sine of 1/2 theta. Y equals sine of 1/2 theta. And that's how I find the b value to put in my equation given the period that I can find from this graph. Okay, let's do a couple more. This one right here, I start at the origin, so I know this is going to be a sine function. So I'm going to go through one full rotation here and end up at pi. So the period of this function is pi. Well, period is equal to 2 pi, or the original period, divided by b. So b is equal to 2 pi over pi. Those pi's cancel. I'm left with just b equals 2. So my period is my period is pi, so my b value is 2. So my function ends up being y equals sine of 2 theta. And just to double check, if I was given this equation, then the period would be 2 pi over b, which is 2 in this case, giving me a period of pi, which is indeed the period of this function. Okay, number 4 here, I have starting at a maximum here, this is going to be a cosine function. So I go down and back up again to the starting point, and it takes 6 pi radians to get there. So if my period is 6 pi, then my b value is 2 pi divided by 6 pi, which reduces to 1/3. So my equation is y equals cosine of 1/3 theta. And that's my equation. So that's how we find the period. That's how we determine the period, either given an equation or given a graph. That's how we define the period, and that's how the period can be expressed as a transformation in a trigonometric function. Okay, so about 20 minutes in, now I'm going to just do a handful of homework problems, specifically some tangent problems that we didn't go over really in the meat of that lesson. So either using degrees or radians, depending on what's given to me here on the graph, I'm going to find the period of the function and then graph it. So right here, y equals sine of 2 theta. Period for a sine function is 360 degrees over b, or in this case divided by 2. And I'm using 360 degrees because everything is in degrees on this graph. 360 divided by 2 is 180. So sine function starts at the origin. It better end again at 180 degrees here. We'll take one full cycle to get from 0 to 180 degrees. So my function is going to look something like that. Doesn't have to be perfect, and if you want to keep going, you can. It better make another full rotation in another 180 degrees, all the way to 360 here. So that would be my graph, with my period being 180 degrees. Sorry, my period being 180 degrees. Makes a full rotation from 0 to 180. Okay, we haven't encountered a tangent problem yet, but let's just remind ourselves that the traditional parent tangent function would have an asymptote every, 180 degrees, because the period is 180 degrees. So let's find what the period of this new function would be. The period of a tangent function is 180, because that's the period of a parent tangent function, divided by b, or in this case, divided by 1/2. 180 divided by 1/2 is the same as 180 times 2 over 1, which is 360. 360. So now, instead of having an asymptote at 90, 270, 450, etc., we're going to have an asymptote at 180, and then 360 plus 180, which is, I can do math, I promise, 360 plus 180, which is 540. So we're going to have asymptotes right here, 360 degrees apart. And my tangent crosses the x-axis at 0, 360, and then it would cross again at 720, etc., etc., etc. So my tangent function would look something like this. Because the period is 360 degrees, I cross the x-axis at 0, and then again at 360 degrees, with the asymptotes being halfway in between. So here at 180 degrees, and then at 540 degrees, etc., etc. So that's how I graphed that tangent function. Okay, now these are some more homework problems, 28 and 30. Given a graph, we're going to find the period and write what the equation would be. So here I have this function right here. I'm starting at a maximum, so this is going to be a cosine function. And it takes, let's see, 8 pi radians to go through a full cycle. So if my period here is 2 pi over b, because I'm using 2 pi because my graph here is in radians, then 8 pi is equal to 2 pi over b, because that's the period of this function. That means that b is equal to 2 pi over 8 pi. When I cancel out my pi's and reduce that fraction, that means b is equal to 1/4. So my function would be y equals cosine, because again I start at maximum, so there's a cosine function, cosine of 1/4 theta. Okay, what about my tangent function? I know this is a tangent function because this is a pretty unique one. My period of a tangent function here is all in degrees, so my period is going to be 180 degrees over b. So how often does this graph repeat itself? Well, I go from 0 to 90 to 180, etc. So my period is 90 degrees. That's how long it takes to repeat itself. So period is 90 degrees, so 90 is equal to 180 over b. Or b is equal to 180 over 90, which is equal to 2. So my function here is going to be y equals tangent of 2 theta. Y equals tangent of 2 theta. And that's it. That's how we determine the period of a function. So real quickly, traditionally we have another lesson after this combining midline, that vertical shift, and amplitude and period all in one equation. So I just want to give you an idea of what that would look like. So here, for example, I have y equals a sine of bx plus c. So when I change the b value, it changes the period. When I change the a value, it changes the amplitude. When I change the c value, it changes the midline. So I'm just going to play all these for fun so you can see it change in real time. So you could, if need be now, construct an equation or a graph of a trigonometric function that has all these different transformations applied to it. Either a midline change, an amplitude change, or a period change. You could have a function with all of those transformations applied and be able to identify what those graphs look like. Okay, I've had my fun. Let me pause all of these. So again, by the end of this video, this is what I hope that you're able to do. I hope you're able to determine the period of a trig function given an equation, and then graph the period from that given trig equation. And then I hope that if I were to give you a graph, that you could write the equation of that trig function with the period change. So that's all I got for you. This is the end of Unit 12 for now. I hope that was helpful. Please reach out to me with any questions that you might have. I hope that you enjoyed that as much as I did.